Alright, what's up guys? In this video, I'm going to pick up with some multivariable calculus. We're going to be talking about Fubini's theorem. So we just have to use Fubini's theorem to evaluate the double integral or the iterated integral once we set it up. And they want us to integrate using both possible orders. So we got our double here, integral here. R is the rectangular region. So this is Fubini's theorem here. And without basically reading word for word everything on this theorem, basically what it allows us to do, it allows us to evaluate double integrals over rectangular regions by setting up what are called iterated integrals. An iterated integral is basically when the limits of integration are defined, like we are given some double integral and it already has the limits attached to it. And you know, we know what that is. And basically what Fubini's theorem, it says that we can integrate in any order we want and get the same answer. So we can integrate dxdy, we'll get the same answer. Let's just say, hypothetically speaking, let's say we had some double integral when we set it up as an iterated integral using Fubini's theorem. Let's say we integrate dxdy, okay, and again, it's over a rectangular region. If we do a dy dx, we should get the same answer. So let's just say hypothetically, if we got -5, well, we should get -5 for this order too. The common issue or mistake that a lot of students make with Fubini's theorem, and I bring this up when we do the second order, is that they don't switch the integrals or line the integrals up correctly with the variables in which they're intending to integrate with respect to first. So in this particular case, if you notice this first integral here, when we want to integrate respect to x, the limits from a to b will correspond to the variable x. The limits from c to d will correspond to the variable y. Well, here's the common mistake, because when students go and do it in the other order, what they'll do is they'll say, okay, well, we're going to integrate respect to y, but then they'll leave the limits, or they'll have the integral from a to b, they'll leave it in there. And as you can see, the limits of integration from a to b do not correspond to y. So if you don't flip the integrals to make sure they match up with the correct differential, you will get the wrong answer. Okay, so that is a common mistake, so make sure you just do that. But other than that, it's not that bad. So let's go ahead and set it up. Now, this works for rectangular regions. General regions, it doesn't really work that way. But for rectangular regions, it definitely, we can use it. So we're going to do it in both orders, and we're going to get the same answer. So we'll just start with dx dy and just kind of see what happens. So let's just do dx dy. Well, if I'm going to do dx dy, then that means that we'll have the integral from 1 to 4, from 0 to 2, and then we'll have x plus 2y, and it'll be dx dy. Now it's just a double integral. So remember, we integrate respect to x first, treating y as a constant. We work our way from the innermost integral to the outermost one. So this would be from 0 to 2. We'll have x plus 2y integrated respect to x. Okay. So keep in mind that this is the integral from 0 to 2, x with respect to x, from 0 to 2, 2y with respect to x. Okay, so we see what we get. Okay, so let's go ahead and do the first one here. So for this first one, from 0 to 2, we got x dx, so this clearly becomes x squared over 2 evaluated from 0 to 2. Okay, and you see what you get from there. So if we sub in the 2, we'll get 2 squared, which is 4. Divide by 2, we'll get 2. So this would be 2 minus 0, which is 2. So this is what we get for that piece. Again, I'm breaking these double integral up into small little steps like this. Once you get the multivariable calculus, you'll be so good with integration, you won't need to break it up in small incremental steps that I'm doing like this. So don't in any way assume that this is how you absolutely have to do it. And what I mean is, when I say absolutely have to do it, you don't actually have to write down all the steps. I'm just doing that for the purposes of the video. So I just wanted I just want to make that clear. Now, when we go over to the other one, and the reason why I want to break this down is because it's very important that I touch on the fact that since we're integrating respect to x, first we're treating the other variable as a constant. So in this case, from 0 to 2, we got 2y dx. Well, not only is the 2 a constant, but the y is also a constant. So we know essentially that this becomes from 0 to 2, we got 2y dx. So essentially what this becomes is 2y multiplied by x from 0 to 2. And you see what you get in that particular case. And then you just substitute in, and we know we're just going to get basically 4y. So this gives us 4y. So now we move to integrating with respect to x now, and it'll be from 1 to 4, and we'll just simply have 2 plus 4y. Now we're integrating respect to y. If I said x, I meant to say y. I apologize. And so this one is very easy. Again, it's just going to be from 1 to 4. We're integrating the constant with respect to y, and then from 1 to 4, we're integrating 4y with respect to y. Okay. So this obviously just gives us 6, and then here, well, it looks like this is going to give me, I think it's going to give me 15 over 2. Okay. And so now what we do is we take let me get another sheet. We take our numbers and we see what we get. So we got that constant that was on the outside, remember? So that's going to be 4 times 15 over 2, and then we'll simplify from there. And this gives me essentially 30. So now what we have is, if we go back, we'll have 6 plus 30, not 15 over 2, which we know gives us 36. All right, so let me just quickly rehash what happened. Okay, so basically here when we broke it up, we integrated from 1 to 4 to respect to y. Again, that's just a constant at 6. The 4 was pulled out, then we have y squared over 2 evaluated from 1 to 4. Where we sub that in, we'll get 8 minus 1/2, which is 15 over 2. And then I multiply by the constant 4 that was pulled out, which when we multiply, that gives us 30. And then we add 6 and 30, which gives us 36, which would actually be the answer for the double integral in the order dx dy. So from 1 to 4, from 0 to 2, and it was x plus 2y with respect to x, and then with respect to y, and the answer is 36. So that's for the first order. Okay. Now we need to do it. We need to do it in the other order. Okay. So with that one, remember we're using Fubini's theorem, so we should get the same answer. If you don't get the same answer, your integration was probably a little off, or check to see that you make sure you have switched the integrals so that they correspond to the appropriate differential. So either one of those two issues could be why you don't get the same answer. Okay, so now we're doing dy dx this time, so we have to change it. So now, since we're doing dy dx, the integral becomes from 0 to 2, from 1 to 4. Okay, and again, we still got our same function, x plus 2y. And this time, it's going to be dy dx. Same scenario in this particular circumstance. So from 1 to 4, at x plus 2y dy. Well, we know if we integrate from 1 to 4, x with respect to y, we're integrating constant respect to y, evaluating from 1 to 4. That'll just simply give me 4x minus x, which is 3x. So we'll essentially get 3x. And then if we integrate with respect to y from 1 to 4 for 2y, well, in that case, we'll pull the 2 out. That's a constant. It'll be y squared over 2 from 1 to 4. Again, that'll give me 8 minus 1/2, which is 15 over 2. Then we need to multiply 2 times 15 over 2, which will give us 15, because 2 times 15 is 30. Divide by 2, that's 15. So this becomes 3x plus 15 when we integrate it. When we integrate it with respect to y. Now, we move to our outermost integral now, and we do it with respect to x. So now we got 3x plus 15 integrated with respect to x now. And I guess I'll break this one down since I didn't do the first one. Okay, so again, it's just from 0 to 2. We got 3x with respect to x plus the integral from 0 to 2. And we're integrating this constant 15 with respect to x. And we see what we get. So we'll clearly get 2 here. And then here, when we integrate this with respect to x, again, we're integrating constant respect to x from 0 to 2. And in this case, we just get 30. So once we took that 2 there, and we'll multiply by 3, so the 3 was pulled out. So this becomes 6. And now we got 6 plus 30, just like we did last time. And we simply get 36. So let me break down the work for you and what I did. So remember, the 3 was pulled out. This becomes y squared over 2 from 0 to 2. And again, this just essentially becomes 2 minus, this becomes 2 minus 0, which is 2, multiplied by the constant 3. So I'll get 3 times 2, which is 6. Maybe I should have wrote it that way. I always kind of break it up a little bit. So maybe I should have written it a little better than that, so I apologize. Because what I tend to do sometimes off the top of my head is I'll essentially factor out the constant first. And I'm doing the math in my head, but I'm not necessarily writing it down, and sometimes it can be a little confusing. So that's what I did. I multiplied by the constant that I pulled out. So that's my fault on that. Should have been a little bit more clear. In this particular case, same, pretty much same scenario. After we did the multiplication, or after we did the integration from 0 to 2, it would have been, again, 15 is a constant. And we're integrating respect to x, so it'd just be 15 multiplied by x from 0 to 2, which is 30, which when we plug it in, we'll get 30, because it'd be 30 minus 0, which is 30. And then we add the 2, we'll get 36, which is the exact same thing that we got for the first integral. So from 0 to 2, from 1 to 4, x plus 2y, dy dx is obviously going to be 36, just like the upper one was. And that's Fubini's theorem. All right, so that would be final answer number 1, or final answer number 2, actually. And this would be final answer number 1. All right, so let me know if you got any questions about it, and we can talk about it. So I'll see y'all next time.